In this lesson, we begin our studies in probability, specifically empirical and theoretical probabilities. Let's start with a definition. The first definition that we look at is the definition of an experiment. An experiment is a controlled operation that yields a set of results. Some examples that we may look at in this lesson is like flipping a coin. That's an experiment. Or rolling a single die. That's an experiment. Or drawing a card from a deck of cards, from a 52 card deck of playing cards. That's an experiment. Or a medical researcher administering an experimental drug to patients to determine their reactions. That's an example of an experiment. The next definition is outcomes. So these are the possible results of an experiment. For example, the outcomes of flipping a coin, right? You can get heads or tails. These are the outcomes. Or the outcomes of rolling a single die, of course, are the numbers 1, 2, 3, 4, 5, and 6. These are the possible outcomes. The outcomes of drawing a single card from a deck of cards. There's 52 different cards, right, in a standard deck. So these are your possible outcomes. With that example of administering an experimental drug, the outcomes may be a favorable reaction or no reaction or an adverse reaction. So these are examples of outcomes. Next, we have an event. What we mean by an event is a sub-collection of the outcomes of an experiment. For example, when a coin is flipped, an example of an event would be you getting heads, or a different event would be getting tails. When a single die is rolled, now there are many different events that could happen when a single die is rolled. For example, rolling an even number. Every time you rolled an even number, that would be an event. Or, I don't know, rolling a number less than 4. Or rolling a 5. Rolling a number greater than 2. You get the idea. There's different types of events that could happen when we're talking about rolling a single die. When you're talking about a card that is drawn from a standard deck of playing cards, there are many different events that could occur, like drawing an ace, or drawing a face card, or drawing a club, or drawing a red card. These are different events that could happen. When a researcher administers an experimental drug, one example of an event is the patient having a favorable reaction to the drug. So these are a sub-collection of the outcomes of an experiment. Now, once we understand experiment, outcomes, and event, and what we mean by these terms, we can then talk about and understand or discuss probability. The probability of an event is a numeric measure of the likelihood that the event will occur. When we talk about events or an event, we usually use the letter E to represent an event. And the probability of the event occurring is denoted like this: P of E. This is P of E. That's how we read it, and we understand it to mean the probability of this event occurring or happening. Now, there's two different classifications that you and I will study when it comes to probability. One of them is empirical probability, and the other is theoretical probability. Now, empirical probability, which is also called experimental, empirical probability is the relative frequency of occurrence of an event and is determined by actual observations of an experiment. Determining the chance of something happening in the future by observing past results is called empirical probability. Now, this is different than theoretical probability. So theoretical or mathematical probability is determined through a study of the possible outcomes that can occur for the given event or given experiment. Okay, let's first discuss empirical probability. The emphasis later on in this lesson will be on theoretical probability, but let's first start here. Empirical probability, or sometimes called relative frequency. Okay, so we have a formula for empirical probability of an event. Remember, this means the probability that an event will occur, okay? And we have a formula. The probability of an event occurring is equal to this ratio or this fraction. In the numerator is the number of times the event E has occurred divided by, in the denominator you have the total number of times the experiment has been performed. So what's really important is that the probability of an event, P of E, this entire number here, this entire fraction, will always be a number between 0 and 1, inclusive. You can express it as a decimal or a fraction, okay? But the empirical probability of 0, for example, indicates that the event has never occurred. So if this formula gives you 0, if your answer is 0, that means the event has never occurred. If this ratio or this formula, this fraction is equal to 1, that means the event has always occurred. So remember that this will always be between 0 and 1 inclusive. All right, let's look at our first example. At a Little League concession stand, the last 40 beverage purchases were as follows: 16 bottles of water, 14 bottles of sports drink, and 10 bottles of soda. So using this information, determine the empirical probability that the next beverage purchased is a bottle of, let's do the first one, water. Okay, so this is for part A, okay, everybody? For part A. So P of E. Okay, in this first one, E represents the event that a bottle of water is purchased. Okay, that's what E represents. That the next purchase is the bottle of water. All right, according to the formula, which is still on the screen here, the numerator is the number of times this event has occurred. So if you look at the information, it happened 16 times. There were 16 cases or 16 occurrences of water being purchased over the total number of times the experiment has been performed. In other words, how many purchases total? Well, 40 was given, right? 40. So 40 is your denominator. Okay. If you simplify remember to simplify a fraction, you find the GCF, the greatest common factor. The largest number that is a common factor of 16 and 40 is 8. So I'm going to divide by that GCF, right? So always simplify. So then this empirical probability, P of E, is equal to 2/5. Notice that 2/5 is greater than 0 but less than 1. 2/5 is almost 1/2. In order for it to be 1/2 exactly, the numerator has to be exactly half of the denominator. That means the numerator would have to be 2.5, because that's half of 5. So this numerator is really close to 2.5, and so this value is really close to 50%. Okay, so 2/5. This is the probability, right? Almost 50%. This is the probability that the next beverage purchased will be water. All right, let's do the sports drink. So let's see. All right. I'll change colors here. All right, here it is. This is for the sports drink. The denominator is going to be the same, everybody, because that's how many purchases were made, right? Total. But as far as sports drink, 14, right? 14 of the 40. 14 of the 40 were sports drinks. So let's simplify. We're dividing this time by 2. 2 is the GCF. 14 divided by 2 is 7. 40 divided by 2 is 20. So this is the probability that the next purchase will be a sports drink. Now, this value is between 0 and 1, of course, always. But notice that this is much less than this value. We talked about how this value, 2/5, is really close to 50%. It's a little bit less than 50%, but this value is actually less than 50% as well, because again, in order for this to be exactly 50%, the numerator would have to be exactly half of the denominator. Half of 20 is 10. 7 is less than 10. So this value is indeed less than 50%. Oh, by the way, folks, if you were to change this fraction so that it has the same denominator as 20, you can multiply by 4 just to get an idea of how close these numbers are. So then this 2/5 is equivalent to 8/20. Okay, so this probability here is indeed less than the previous probability. I said much less. I take that back. It's not much less, but it is indeed less than the previous number. But I don't want to confuse anybody. 2/5 was the answer for the previous problem. And now 7/20 is the probability of the second one, which is for a sports drink. All right, let's go for the third event, which is soda. Okay, let's move this up a little bit. All right, P of E. Now in this case, E is the event that soda will be purchased. Again, the denominator doesn't change. There are 40 purchases altogether. But if you look at the data, it's 10 bottles of soda that have occurred. So let's simplify this. Divide the numerator and denominator by 10, and you get 1/4. So 1/4 is the probability, and 1/4 is 25%. So this is the lowest probability out of all three, okay? One thing I want you to notice is that every single fraction that was given here, I simplified each one, all right? So we always want to write our fractions in simplest form, or our book says lowest terms. Also, you could write these fractions as decimals if you prefer. If you want a decimal, just divide. Let me create some space here. So 2/5. So there's a couple different ways to write this as a decimal. Remember, a decimal is a fraction whose denominator is a power of 10. And so if you were to multiply this by 2, like this, because you want the denominator to be a power of 10, then this fraction here is equivalent to 4/10, which is 0.4. Oops, sorry, hold on. Let me see if I can rewrite this better. All right, so 0.4 is 2/5, but written as a decimal, okay? Remember that a decimal, again, is a fraction whose denominator is a power of 10. I can change 20 to be 100 if I multiply by 5, of course, in the numerator and denominator. So then this would be equal to 35 over 100. So this is equal to 0.35. This would be 7/20 as a decimal. And finally, a quarter. A quarter can be rewritten as, let's see, if we multiply the numerator and the denominator by 25, we get 25 over 100, which is 0.25, which is 25%, right? Which is what we said earlier. And so anyway, you can do this, or you can just simply pull out a calculator and just punch 2 divided by 5 in your calculator, or 7 divided by 20 in your calculator, or 1 divided by 4. What was I going to say? Oh, that's right. I was going to say this. You know how I made this fraction to have a denominator of 10? I could have, like I did the others, made the denominator to be 100. So let me go back and show you that. Just want to make sure we're clear about this. You're going to get the same decimal. But if you wanted 100, 10 is good enough. But if you wanted 100, you have to multiply by 20. And then you get 40 over 100, which is 0.40, which is equivalent to 0.4. You don't need that 0, that terminating 0 there. So anyway, it's the same decimal. It's equivalent. Check this one out. A pharmaceutical company is testing a drug that is supposed to help reduce high blood pressure. The drug is given to 500 individuals total, okay, with the following outcomes. 379 people reported that their blood pressure was reduced. 62 people had their blood pressure unchanged, so nothing changed. And 59 people, their blood pressure actually increased. If this drug is given to an individual, determine the empirical probability that the person's blood pressure is reduced, unchanged, or increased, and write your answer as a decimal. All right, so let's go for it. And this is bothering me. This S here should have an apostrophe. The person's blood pressure. All right, cool. All right, here we go. For part A, the event, capital E, stands for the person's blood pressure being reduced. All right, here we go. So this is the answer for part A. The probability of the person's blood pressure being reduced is equal to. Now, we know that the denominator is 500 because that's how many total experiments there were, right? There were 500 individuals total. But out of those 500 different experiments, 379 came through as their blood pressure was reduced. So this is the answer. But as a decimal, just punch this into the calculator. You get 0.758. Remember that your probability has to be a number between 0 and 1. Okay, if you ever get something less than 0, or if you get something less than 0 meaning negative, or if you get anything greater than 1, something is wrong. Okay, so this is the answer for the probability that if I wanted to take this medicine, okay, this drug, I can change this to a percentage, 75.8%. There's a 75, let's just say about 76, right? About 76% chance that it's going to work for me, that my blood pressure will be reduced. Okay, let's go for the next one. Now we're talking about the probability that, capital E here, P of E, E this time represents that my blood pressure will stay the same. It's not going to go up and it's not going to go down, all right? So this is equal to, again, the denominator stays the same because that's how many total experiments there were. But 62 people, after taking the drug, had their blood pressure unchanged. This as a decimal is 0.124. So, I mean, this is good news. I mean, as a percentage, this is a little bit more than 12% of a chance that the drug will basically not do anything for you. Your blood pressure won't go up, but it also won't go down. All right, last one. P of E. This time, E, the event we're talking about, is your blood pressure actually increasing, which is horrible, right? You would want, so you're trying to take a drug that lowers your high blood pressure, and you have an adverse reaction to it, right? The opposite ends up happening. This is very unfavorable. So anyway, 59 people are upset, really, right? Because their blood pressure ended up increasing. So this is the probability. As a decimal, it is 0.118. If I were to write this as a percentage, again, to change a decimal to a percent, just multiply by 100, which means the decimal just moves twice to the right. So as a percentage, this would be 11.8, which is almost 12%. Almost 12% that your blood pressure would actually increase. This is the lowest probability. This is the middle valued probability. The highest probability by far is this one here, which means you are more likely to have your blood pressure reduced by taking this drug than any other outcome. Now, what's really important is empirical probabilities are used when there is enough data from past events to reasonably predict similar future events. For example, life insurance companies, right? Life insurance companies use data gathered over many years and empirical probability to determine the likelihood that an individual in a certain profession with certain risk factors lives to be the age of, 75, right? So they're using empirical probabilities to assess this risk. In general, empirical probability is used when probabilities cannot be theoretically calculated or mathematically calculated. Now, to lead us to something called the law of large numbers, let us consider the following kind of predicament or situation. Let's talk about having a fair coin. A fair coin meaning a coin that where on one side is heads and the other side is tails, okay? It's reasonable to accept that if a fair coin is tossed many, many times, it will be heads approximately half the time. Intuitively, we can guess that the probability that a fair coin will be heads is 1/2. But does that mean that if a coin is tossed exactly twice, that it will be heads exactly once? No, not necessarily, right? If a fair coin is tossed 10 times, does that mean necessarily that we will have 5 heads exactly? No, not necessarily. So then what does it mean when we state that the probability that a fair coin will be heads is 1/2? What do we mean by that? All right, so let's look at the following data that has been collected. All right, so let's look at this data. So this is a bunch of experiments, all right? And the data and all the outcomes have been documented. All right, so let's say the coin has been tossed 10 times. Because it's a fair coin, we expect the probability of getting heads is 1/2. So if there are 10 tosses, we expect 5 heads. But after tossing the coin 10 times, we actually got 4 heads. So the relative frequency of heads, the probability, P of E, right? Probability of that event happening is 4 out of 10, which is 0.4, which is 40%. Okay, 0.4. Not quite 1/2. After tossing the coin 100 times, we expected to get 50 heads, but we actually got 45 heads. So the relative frequency is 45 over 100, which is 0.45. Notice that this probability is actually closer to 1/2 than before. 1,000 coin tosses, we expected to get 500 heads. We actually got 546 heads. So 546 divided by 1,000 is 0.546. Again, close to 1/2, actually closer to 1/2 than we were before. 10,000 coin tosses. We expected to get 5,000 heads, right? Exactly half of 10,000. But we actually got 4,852 heads, which gives us a relative frequency of heads as 0.4852. Really close to 1/2, closer than we've ever been. Now 100,000 coin tosses. I hope you see the pattern here. We expected to get 50,000 heads. We got 49,770 heads, which gives us a relative frequency of 0.49770. The point of the matter is that the relative frequency, which is the empirical probability, is getting closer and closer and closer to 1/2 or 0.5. The more the more times we toss the coin. So as this number here increases, the more we toss the coin, the higher the number of experiments, then the closer we get to getting a probability of 1/2. This leads us to something called, very important in probability, called the law of large numbers. The law of large numbers states that the probability statements apply in practice to a large number of trials, not to a single trial. For example, like that coin toss we were just talking about, when we say the probability of getting heads for a fair coin is 1/2, what we mean by that is in the long run. After many coin tosses, yes, the probability is 1/2, yeah? But not to just a single trial. It is the relative frequency over the long run that is accurately predictable, not the individual events or precise totals. For example, if we said that the probability of rolling a 2 with a single die is 1/6. What is that? What would that mean? Remember, on a single die, you have the numbers 1, 2, 3, 4, 5, 6. And so there's 1, 2 out of 6 numbers, right? So the probability of rolling a 2 is 1 out of 6, 1/6. What would that mean? It means that over the long run, on the average, 1 of every 6 rolls will result in a 2. All right, when we say equally likely outcomes, we mean that if each outcome of an experiment has the same chance of occurring as any other outcome, we say the outcomes are equally likely outcomes. Like, for example, in rolling a die, the possible outcomes are what? 1, 2, 3, 4, 5, 6, right? If the die is a fair die, then it is equally likely that you will roll any one of the 6 possible numbers, right? That's equally likely. When we flip a fair coin, 2 outcomes are heads or tails, right? Since the chance of flipping a head is the same as flipping a tail, the results of that experiment are equally likely outcomes. When we draw a single card from a standard deck of cards, you know there's 52 different cards, 52 different cards that can be drawn. So since the chance of drawing any one card is the same for all 52 cards, these are equally likely outcomes. Okay, so now we have a formula for calculating theoretical probability. The theoretical probability of an event, P of E, can be determined using the following formula. In the numerator, you have the number of outcomes that are favorable to E over the total number of possible outcomes. For the rest of this lesson, and for many lessons to come, whenever we use the word probability, we are referring to theoretical probability, okay? Okay, a fair die is rolled, okay? Determine the probability of rolling a 2, an even number, a number greater than 3, a 7, or a number less than 7. All right, let's do this one at a time. Now remember, a fair die means you have six equally likely outcomes. You can roll a 1, a 2, a 3, a 4, a 5, or a 6. Okay? So here we go. Let's go for the first one. Here we go. All right, so rolling a 2. So P of E. This is for the first question, okay? Rolling a 2. So E here, E stands for the event that I roll a 2. All right? So the numerator is the number of outcomes favorable to E. Now, if you think about the outcomes, you have 6 different outcomes, but there's only one favorable outcome, and that is rolling a 2. There's only one possibility of getting a 2, right? 1 out of 6, right? So my numerator is 1. That's one favorable outcome. Over total number of possible outcomes is 6. There's 6 different possibilities. So 1/6 is the probability that I will roll a 2. All right, good. Let's go to the next one. P of E. This time, capital E stands for the event that I will roll an even number. Now let's talk about an even number. Your even numbers between 1 and 6 are 2, 4, or 6. That means there are 3 favorable outcomes, rolling a 2, a 4, or a 6, out of 6 total possible outcomes. So then this is 1/2. So rolling a fair die, you have 1/2. The probability is 1/2 that you will roll an even number. All right, let's go for the next one. Rolling a number greater than 3. All right, this time around, E, my E's are getting sloppy here. This time around, E represents rolling a number greater than 3. Now think about a die. What are the numbers greater than 3? 4, 5, or 6. So that means there's 3 favorable outcomes out of 6 total. So the probability of us rolling a number greater than 3 is 1/2. All right, next, P of E. This time around, E represents the event that I will roll a 7. A 7. Now, this is funny because if you think about a die, there's no 7. It's 1, 2, 3, 4, 5, or 6. So there are no favorable outcomes out of 6 total. So 0 is the probability that you're going to roll a 7. In other words, it ain't gonna happen, right? That's the that's the interpretation there. All right, one last one for us, and that is the probability of the event E happening, which in this case is a number less than 7. How many numbers on a fair die are less than 7? All of them. 1, 2, 3, 4, 5, 6. They're all less than 7. So you got 6 favorable outcomes out of 6 total outcomes, which is 1. So your probability is 1. In other words, you will for sure, rolling a fair die, you will for sure roll a number that is less than 7. That will always occur. One thing I want us to notice is that all of these probabilities are between 0 and 1 inclusive. All right, so we have some important probability facts. Number 1, the probability of an event that cannot occur, like us rolling a 7, is 0. The probability of an event that must occur, like rolling a number less than 7, is 1. Every probability is a number between 0 and 1 inclusive. What we mean by that is P of E must be greater than or equal to 0, less than or equal to 1. Okay? The sum of the probabilities of all possible outcomes of an experiment is 1. All right. The names of 9 birds and their food preferences are listed below. Each of the 9 birds' names is listed on a slip of paper, and the 9 slips are placed in a bag. One slip is to be randomly selected from the bag. Determine the probability that the slip contains the name of any kind of finch, the probability that the slip contains a bird that has a high attractiveness to cracked corn, the probability that the slip contains the name of a bird that has a low attractiveness to peanut kernels and a low attractiveness to cracked corn, and a high attractiveness to black striped sunflower seeds. And finally, the probability that the slip contains the name of a bird that has a medium attractiveness to either peanut kernels or cracked corn or both. All right, so let's do this. Let's answer the very, very first one. Now, let me move up here so that you can see the entire. Okay, good. I hope you can see it all there. Out of the 9 birds that are listed, how many of them are finches? 2. You have the American goldfinch and you have the house finch. So out of 9 birds, 2 of them are favorable because that's what we're considering at the moment, a finch. What's the probability that one of them would be a finch? So for part A, everybody, we're writing our answer like this: the probability that the slip contains a bird that is a finch, right? All right, so here we go. Let me finish this off. This is equal to, there are 2 favorable outcomes out of 9. So then that's our answer for part A. 2/9 is the probability that that we're going to choose a finch when we pull a random slip of paper out of that paper bag. All right, next, part B. What's the probability that the slip contains the name of a bird that has a high attractiveness to corn? All right, look at your table. How many of the birds have a high attractiveness to cracked corn? Let's count. 1, the common grackle. That's it. Out of all the 9 birds, there's only 1 that has a high attractiveness to cracked corn. So for part B, we have the probability that the slip that we randomly choose has a bird that has a high attractiveness to cracked corn would be 1 favorable outcome out of 9 total. So that's the probability. All right, let's go for this one now. A bird that has a low attractiveness to peanut kernels, a low attractiveness to cracked corn, and a high attractiveness to black striped sunflower seeds. So what we need to do is look at the table, read across the rows, and find how many birds satisfy these conditions. Look at the American goldfinch. It has a low attractiveness to peanut kernels, a low attractiveness to cracked corn, and a high attractiveness to black striped sunflower seeds. So the American goldfinch is 1 favorable outcome. Look at now the evening grosbeak. It's the same thing. Low, low, high. All right, so that's 2 favorable outcomes. Finally, look at, the northern cardinal. Low, low, high. So out of 9, there are 3 favorable outcomes. All right, everybody. Instead of writing it all out, low attractiveness to peanut kernels, I just said low to peanuts. Instead of saying low attractiveness to cracked corn, I just said low to corn. And then high to black striped sunflower seeds. Anyway, we found that looking at the table, that there were 3 favorable outcomes out of 9. We have to simplify this, divide the numerator and denominator by the GCF of 3. So 1/3 is our probability. All right, let's go to the last one. We want to find all the birds that has a medium attractiveness to either peanut kernels or cracked corn or both. All right, so let's look at the blue jay. The blue jay has a medium attractiveness to cracked corn. Okay, so that's one. Look at the chickadee. The chickadee has a medium attractiveness to peanut kernels. So that's two. Let's look at the common grackle. It has a medium attractiveness to peanut kernels. Let's look at the house finch. It has a medium attractiveness to peanut kernels. Let's look at the house sparrow. It has a medium attractiveness to cracked corn. Let's look at, let's see, what else? We just did the house sparrow. What about the mourning dove? The mourning dove has a medium attractiveness to cracked corn. So we're looking for peanut kernels or cracked corn. So I counted, is that all? Did I lose count? Let's see. The blue jay, 1. The chickadee, it's 2. The common grackle, that's 3. Yep. The house finch, that's 4. The house sparrow, that's 5. And the mourning dove, that's 6. All right, so I counted 6, everybody. Hopefully you agree. So let's do this. So let's see. All right, so I just put medium to peanuts instead of peanut kernels, or cracked corn, okay? So anyway, we counted 6, right? 6 out of 9 total. Divide by the GCF, which is 3, and so this is 2/3. That's the probability. All right, cool. Now, in any experiment, an event must either occur or not occur, right? So either that something that you're looking at either is going to happen or it doesn't happen, right? So the sum of the probability that an event will occur and the probability that it will not occur is 1. So in other words, if we call the event capital A, the probability of A happening plus the probability of A not happening must equal 1. Said another way, the probability of event A not happening is equal to 1 minus the probability of that event happening. For example, if we know that the probability that event A will occur is 5/12, that's the probability that it's going to happen, 5/12, then the probability that the event will not occur is 1 minus 5/12, which is equivalent to 7/12. Similarly, if the probability that event A will not occur is 0.3, then the probability that event A will occur is 1 minus 0.3, or 0.7. Okay, folks, I think this might be our last example. Consider a standard deck of 52 playing cards. The deck consists of 4 different suits: hearts, clubs, diamonds, and spades. Now, each suit has 13 cards. 13 times 4, that would be 52 total cards, including the number 1, which is the ace, through 10, and 3 face cards: the jack, the queen, and the king. So each suit, the hearts have all of those, the clubs, the diamonds, and the spades have numbered cards 1 through 10. Remember, 1 is the ace, and then the 3 face cards: jack, queen, and king. Hearts and diamonds are red. Clubs and spades are black cards. There are 12 face cards altogether: 4 jacks, 4 queens, and 4 kings. Okay, one card is to be randomly drawn from the deck of cards. Determine the probability that the card drawn is an 8, not an 8, a club, a jack or queen or king, so basically a face card, a heart and a spade, a card greater than 5, and less than 9. All right, so let's do it. Let's do, obviously, one at a time here, folks, okay? So here we go. Let's do the probability that the card drawn is an 8. So there are 4 different suits. So there's an 8 of hearts, there's an 8 of clubs, there's an 8 of diamonds, and an 8 of spades. In other words, there are 4 different 8s. And so the probability of us choosing randomly a card that is an 8, the probability of choosing an 8, there are 4 favorable outcomes out of 52 altogether. This simplifies to 1/13. So this is the answer. This is the probability, folks, that you would choose an 8. All right, let's go to the next one. What is the probability of not an 8? Not an 8. Well, we already know what the probability is for us choosing an 8, so it'll be 1 minus the probability of choosing an 8. That is to say, 1 minus 1/13, which is 12/13. So right now, this tells me this probability is really close to 1. Therefore, it is very likely that when I choose a card at random, that the card is not going to be an 8. That is very likely going to happen. It's actually going to be kind of rare that I would choose an 8. Okay? All right, let's go to the third one. What's the probability that we choose a club? How many clubs are there? Well, remember there's 4 suits. 4 suits, and each suit has 13 cards. So the clubs have 13 cards in them. So there's 13 clubs altogether. Let me see if there's room. The probability of us choosing a club. So there's 13 favorable outcomes because there's 13 clubs out of 52. This simplifies to 1/4, which is 25% or 0.25. So it is, I don't know, I wouldn't say very likely. It's somewhat likely that when we choose a card at random that it would be a club. All right, what about the fourth one? What's the probability that the card we choose is either a jack, a queen, or a king? Basically, one of the face cards. If you read this, there are 12 face cards altogether, folks. 12 out of how many? 52. So the probability of a face card, of course, this means a jack, a queen, or a king, is 12 altogether, 12 face cards out of 52, which is 3/13 after you divide by 4 in the numerator and in the denominator. All right, cool. Now, what about this one? What's the probability of us choosing a heart and a spade? Wait a minute. Is there such a card? Can you choose a card? Can you find a card that is both a heart and a spade? No. You're either a heart or you're a spade or you're a club or you're a diamond. In a standard deck of cards, you cannot be a heart and a spade. So the probability of a heart and a spade, all right, like that, is 0. There is no such card in the entire deck that is a heart and a spade. So this is the probability of 0. In other words, this event can never occur. All right, the last one. What's the probability of the card that we choose at random that it is greater than 5 and less than 9? Greater than 5 and less than 9. Now, the cards that are both greater than 5 and less than 9 are 6, 7, and 8. And there are 4 different 6s. There's 6 of hearts, the 6 of clubs, the 6 of diamonds, the 6 of spades. There are 4 7s. 7 of hearts, 7 of clubs, 7 of diamonds, 7 of spades. There are 4 of 8s. There's an 8 of clubs, 8 of hearts, 8 of spades, 8 of diamonds. So there's the number 6, the number 7, and the number 8. These are the 3 numbered cards that are greater than 5 but less than 9. And there's 4 of each one of those. So, let's see if I'll go with the red again. the probability of greater, that's the word greater, greater than 5 and less than 9. Okay, I know that's sloppy, but there are 12 altogether, right? Because there was 3 numbers, 6, 7, and 8. In each one of them, there's 4 of each for the suits. And so 12 out of 52, which simplifies to 3 over 13. So that's the probability for the last one. That was fun.